Section 5.4 was the first part of the fundamental theorem of calculus. Section 5.5 is the fundamental theorem of calculus part 2. I'm going to abbreviate that FTOC. Part 1 is, and these aren't always in the same order in every text, but in our text, part 1 is the link between the signed area, and I've got here the notation. This is the definite integral notation. The signed area under a curve over the interval from A to B, which, if you recall, we introduced with Riemann sums and counting up discrete areas and limiting as the rectangles or the areas got thinner and thinner and thinner. It's a link between the signed area and antiderivatives, which, if you recall when we introduced that, was the undoing process of antidifferentiation. And if you think about those two notions, area under a curve, counting it up and limiting the number of rectangles to infinity, and undoing derivatives, seem to have nothing in common. And if you've seen calculus before, it's tempting to think, oh, of course they're related, because that's the way I learned calculus. But we learned these two things distinctly: the signed area in the context of Riemann sums, and undoing derivatives in the context of saying, hey, is this a function that's obviously the derivative of someone? So what the fundamental theorem of calculus part 2 says, so part 1 is big, it's a big deal. It tells us essentially that if we can find an antiderivative for a function, we can compute a definite integral quite easily without having to go through all the rigor of writing up a right hand or a left hand or a midpoint Riemann sum and then limiting as the number of rectangles go to infinity. Essentially what part 1 says is just find that definite integral, or to find that definite integral, just find an antiderivative and evaluate it at the right-hand endpoint, subtract off what you get when you evaluate it at the left-hand endpoint. Much easier than limiting Riemann sums. Fundamental theorem of calculus part 2 states that if you've got a continuous function on an open interval, and little a is just some real number in the interval, then we get to make a conclusion about the area function. But I want to pause right here for looking at this area function. We'll come back to what the conclusion is about it. This is a totally new kind of function. Notice that the independent variable is x, and it appears here in the expression of the function. And you're experienced with the independent variable appearing in various places. For example, just as an example, you've seen, let's call it g of x since we're using f. G of x is equal to e to the x, so the independent variable appears in the exponent. Or you might have seen h of x is equal to the natural log of x. The independent variable appears sitting next to the letters ln. That indicates take the natural logarithm of the independent variable x. This is a new kind of function that you've not seen before. Here's the independent variable x, and it appears as the upper limit of integration in this expression. So essentially, this is called an area function because depending on what x is, and you've got this starting point a of x is the function that racks up all the area under the curve f up to the independent variable. So essentially, you get to change that right-hand endpoint of your function. You get to change the right-hand endpoint where you stop accumulating area. Brand new function, never seen this one before. We've never seen that independent variable appearing as the upper limit of integration. So then you might wonder, well, every function that we've talked about, we've been interested in, how do we differentiate it? And that is the conclusion of the fundamental theorem of calculus part 2. So let me reveal the whole thing. If you've got a continuous function on an interval, and a is in the interval, so here's where that little a appears, then the area function, which is defined this way, integral from a to x, f of t dt, notice we've got to have a different variable than x for the variable of integration. This area function is an antiderivative of the function f on I. That is, if we differentiate this thing, this definite integral looking thing, if we differentiate it, what we get is f. When we take the antiderivative, when we take the derivative of an area function defined this way, we get the integrand evaluated at x. In other words, and here's just, it's in other words, but it's really in other notation, the derivative with respect to x of the area function, where the upper limit of integration is the variable that you're differentiating with respect to, is just f of x.